Hello, hello, hello. Good afternoon. Good afternoon. So, we have a presentation here Fundamentals of Quantum Computing from April 19th, 2023. This is actually an online workshop on quantum computing by Bernd Baumann. So, this is the agenda introduction, quantum physics, information, bits and qubits, information processing, logic gates, algorithms, doggy bag. Okay, and there are lots of cool stuff. We're going to skim through some of them and maybe take a look into details of some of them. So, representation of numbers, they have discussed decimal number, corresponding binary numeral, physical physical realization. So, we are talking about storage media now. Bit binary digit can be 0, can be 1, a logic state with one or two possible values, and a register with n bits allow the representation of 2 power n figures. So there is an exponential growth, of course. Then we have real numbers, so represented by bit strings of infinite length, but for practical purpose we cannot have infinite length, so we use finite length to approximate real numbers. Bit string ASCII character set, sign representation, some examples like hello world. So HELLO, all of them has their own bytes, of course. So now we come to the definition of quantum bit. Represents a logic superposition state. Alpha 0, beta 1, 0 and 1. These are the basis states where alpha square plus beta square is equals to 1, of course. So these are the probabilities. Then we can also say that beta square equals to 1 minus alpha square. So basically we have just only one parameter, alpha. Then we have an example, classical file transfer example. So file size 100 page, 1 byte 1000 ASCII characters. So LSS idea is to interpret the strings of 800,000 bits. So the entire file, entire thesis, that interpret that as a real number alpha. So you will pass only one parameter. Create a qubit b equals to alpha 0 plus root over minus alpha squares. But of course this qubit cannot be measured just once. It will only give 0 or 1. You cannot measure it just once to find that correct value of alpha. So what can Bob do? Bob cannot reconstruct the cracks from a single qubit. So alpha can be determined from the frequencies of the appearance of 0 and 1 when Bob has measured the qubit for many times. Then we have this example of Schrodinger's cat, a radioactive material, a Geiger counter containing toxic gas, whether it is dead or alive. So there is another issue with measurement, collapse of wave function. What distinguishes the quantum system from measurement device? Then there is the issue of decoherence. So loss of quantum properties by interaction with the surroundings. So these are some things, some open-ended stuff. Then we are moving into logic gates. So simple functions like d to w x, fx equals to y. The calculus d equals to w equals to r is the set of all real numbers. It's information technology, d equals to w equals to b, where b is 0 and 1. It's an example of function from b to b, so binary function. So x can be 0, x can be 1, f1 of x is 0, 0, so it turns it into 0. f2x we have 0, 1, so it is just a replica of x or identity. f3x 1, 0, invert of x. f4x 1, 1, so it is always 1. Alright. So here are some examples. Scalar field in a plane d equals to r square, w equals to r. Vector field in space d equals to w equals to r cube. Then once again we have information technology d equals to b power n, w equals to b to power m. Functions d to w. So here's the domain, w is the range of the function. Now about the logic gates once again. CPUs are built from a multitude of logic gates, of course. A logic gate with n inputs and m outputs is a physical realization of a function f b power n to b power m. So it has n bits to m bits a function. The effect of a gate is described by truth table. So here are some functions where the mapping is from 2 bits to 1. XOR gate, LAND gate, AND gate. Then we have, of course, these are all single bit gates. So similar things are here in quantum gates, single qubit gates. Convert qubits into other qubits. So x equals to alpha 0 plus beta 1. We have a quantum gate which converts it into y equals to gamma 0 plus delta 1. So from alpha beta we move into gamma and delta. The only requirement is that gamma square plus delta square equals to 1. That's it. So gamma is turns out that's the probability of getting 0. Delta turns out the probability of getting 1. So there are many non-trivial single qubit gates. Effect on general state. So this one alpha 0 plus beta 1, so the coefficient that is for this is state 1, this gate changing that for into coefficient for basis state 0. So no standard symbols, line, wire, bus, space, time, curve, x to y function. So here we come to the Hadamard gate. So we apply Hadamard gate to a quantum bit x and we find a quantum bit y. So if the original state was 0, it turns into 1 over root 2 0 plus 1 over root 2 1. But if it was 1, it turns into 1 over root 2 0 minus 1 over root 2 1. So for 0 it is a plus, for 1 it is a minus. So for 0 it is constructive, for 1 it is destructive. So effect on general state. So when we have an x equals to alpha 0 plus beta 1, it turns it into alpha plus beta over root 2 0 plus alpha minus beta over root 1. When we have something like 1 over root 2 0 plus 1 over root 2 1, so this is a superposition, uniform superposition. In that case it becomes so 0 plus 0 constructive inference and 1 gets eliminated because of destructive interference, and eventually you get a 0. Interesting. Similarly, when we have 1 over root 2 0 plus minus 1 over root 2 1 and apply a Hadamard gate, so for the 1 over root 2 0 we get 1 over root 2 0 plus 1 over root 2 1, and then we have minus for 1, and because of destructive interference 0 gets eliminated, we have only 1. That's interesting. So Quanto's classical case: head, we toss a coin, we can get either head and tail, and for both of them, if we toss the coin again, we'll get either head or tail. But for the quantum case, if we have a 0, we will get 0. If we apply Hadamard gate, 1 by root 2 0 plus 1 by root 2 1, then we do the toss again. It's 0 or 1 for case 1, and for each it is 0. Interesting. A little bit different than the classical case. So random numbers applications, Monte Carlo simulations, cryptography, pseudo-random numbers, eavesdroppers can reproduce the random sequence. Then we have real random numbers. So apply Hadamard gates to keep it in state 0. Then I have consumer product, smartphone with quantum chip to generate random numbers for secure communications. So these are some possible applications. Then we have single qubit quantum gates summary. So identity. If it was 0, it is 0. If it was 1, nu is also 1. X, if it was 0, it will be 1. If it was 1, it will be 0. Y, if it was 0, it will be I1. If it was 1, it will be minus I0. Z, so there are 3 dimensions. If it was 0, it will be 0. It will be 1. If it was 1, it will be minus 1. Then we have this Hadamard. For 0, it will be 1 over root 2 0 plus 1 over root 2 1. For 1, it will be 1 over root 2 0 minus 1 over root 2 1. So once again we have multi-qubit gates. Example, NAND gate. Then we have tensor product states, MQ, controlled NOT gate, interesting. Tensor product is interesting. I will see it later again. So control NOT gate is very easy, simple. If the control bit is 0, it leaves the input as it is. If the control bit is 1, it inverts the bit. Then we have entanglement 1. So qubit A and qubit B, product state 1 over root 2 1 1 plus 0 1. Entangled state 1 over root 2 1 0 plus 0 1. Interesting. Product state 1 over root 2 1 1 plus 0 1. 1 over root 2 1 plus 0. Then you can take 1 out of an entangled state 1 over root 2 1 0 plus 0 1. Here is once again another example. Alpha A B plus beta C D. A B and C D. Product state 1 1 or 0 1. Then we have lots of Alice and Bob's results are anti-correlated. So Bob's get the opposite. Similar things for Einstein's hidden variable, spooky action at a distance, Bell type experiments. So the quantum physics is the correct description of nature but against intuition. So cat state before the measurement is entangled. CNOT gate as qubit copy machine. So this is an analogy of CNOT gate with copy machine. So X1 is the master copy, X0 is the empty sheet, Y1 is the master copy, Y0 is the photocopy. X0 is 0, empty sheet. Okay, that's one way to look into it. Then we have no cloning theorem. X1 is alpha 0 plus beta 1 in a superposition. Then we have x1 0 is to alpha 0 plus beta 1 times 0 is to alpha 0 0 plus beta 1 0. Then we have C 0, so alpha 0 0 plus beta 1 1, which is not equals to x1 x1, because x1 x1 will be alpha square 0 0 plus alpha beta 0 1 plus alpha beta 1 0 plus beta square 1 1. So there is this universality principle. Any multiple qubit gate can be composed of CNOT gates and single qubit gates. Interesting. Then we have quantum algorithms. X1, x0, function of x1. Quantum parallelism. X0 is 0 implies x1, x0, 4f. X1 0 tensor product fi x1 equals to x1 fi x1. So a measurement of the output target qubit yields fi0 or fi1. So fi0 tensor product fi1 equals to 1 if fi is balanced, 0 is fi is constant. So balance function. So by balanced, it means in a symmetric superposition between 0 and 1. So we have now come into this Dirichlet problem. How many function evaluations are needed to determine whether a gate has implemented a constant or a balanced function? So classical computer, for functions of the type f b to b, the answer is 2. Only 2 evaluations are needed. So by how many evaluations? So 2 evaluations. Does it mean 2 measurements? At time t1, it got this. So quantum physics allow to solve the differential problem in one iteration. Generalization to functions of the type f b power n to b is possible. Advantage increases exponentially with n because the higher n goes, we still can solve it in one iteration. That's interesting. So this is historically first example of quantum supremacy. And also there is this experimental verification in 2003, but this algorithm has no practical applications. Then we have Shor, Peter Shor, algorithms for prime factorization. Of course, we have it, we know it, we saw it. Then we have Grover's algorithm, which is a search algorithm. It, speed up of MP complete and related problems from order of n to order of root n. We have TSP, unstructured database, quantum counting. So once again, here's a reminder of single qubit quantum gates. I identity 0 to 0, 1 to 1, X 0 to 1, 1 to 0, Y 0 to I1, 1 to I minus I0, Z 0 to 0, 1 to minus 1. Then we have Hadamard H 0 to mapping to 1 over root 2 0 plus 1 over root 2 1, and 1 to 1 over root 2 0 minus 1 over root 2 1. Then we have super dense coding. T1, T2, T3, T4, T5, 6, T6. Example bit sequence. So Alice has to use gate f equals to x on her qubit. Above setting T6, a equals to 0 and b equals to 1. So here's a summary of super dense coding. Alice can transfer the bit combinations 0 0 0 1 1 0 1 1 by applying the appropriate gate. Advantage super dense coding factor 2 requirements. Bob needs to prepare a pair of entangled qubits and send a qubit to Alice. Our advantage is poor. So prepare a pair of entangled qubits, send one of the 2 qubits to Alice. But overall advantage is not that much. So dynamics of quantum systems is described by Schrodinger's equation. Measurement means collapse of a function. Prediction of spectrum or probability of measurement results, linearity and superposition. Quantum systems are sensitive decoherence, entanglement, strange correlations. So information is stored in qubits. Qubits cannot be copied. No cloning theorem. Typical effects like superposition, interference, and entanglement are crucial for efficient computing. Superposition results in quantum parallelism. Parallelism results in quantum supremacy. Quantum supremacy has been demonstrated experimentally. Anybody who is not shocked by quantum theory has not understood it. Niels Bohr. So alright, that's it. So this is the end. So some of the external links here. Quantum computer Qiskit, the Python library. Quantum flagship, quantum GTGist. Alright, this is it.